In September 2023, something happened in the semiconductor industry that was not supposed to be possible. A Chinese company that had been sanctioned, blacklisted, cut off from every major equipment supplier on Earth, and denied access to the most advanced chip-making tools ever created, somehow produced a 7-nanometer processor. And it didn't just produce it in a lab, it shipped it inside a commercially available smartphone that millions of people bought. So how did SMIC do what the entire Western semiconductor establishment said couldn't be done? And why is Intel, the company that literally invented the modern microprocessor, now more afraid of this single chip than it is of any product Samsung or TSMC has ever released? Here's the answer that nobody in the mainstream tech press is willing to say plainly. Because SMIC's 7-nanometer chip doesn't just represent a technical achievement, it represents the complete failure of the most aggressive technology denial strategy the United States has ever deployed against a single nation. And if that strategy has failed at 7 nanometers, the implications for everything that comes next are staggering. Most people think the SMIC story is simple. China cheated, stole some designs, and cobbled together an inferior chip. That's the narrative you hear on Western tech channels and in policy briefings on Capitol Hill. And here's what that narrative gets dangerously wrong. It confuses the method with the outcome. It doesn't matter whether SMIC used older deep ultraviolet lithography equipment instead of ASML's extreme ultraviolet machines. What matters is the result, and the result is a functional 7-nanometer chip fabbed at commercial scale. To understand why this is genuinely miraculous and why it terrifies Intel, you need to understand 3 forces that converge to make this possible. I call them the Sanction Paradox, the DUV Breakthrough, and the ecosystem acceleration effect. Each one individually challenges conventional wisdom about semiconductor competition. Together, they reveal a new reality that the Western chip industry is only beginning to comprehend. Let me start with the first force, the Sanction Paradox, because this is where the entire story begins and where the West's strategy broke down in a way nobody predicted. In October 2022, the Biden administration launched the most comprehensive semiconductor export controls in history. The Bureau of Industry and Security issued rules that block China's access to advanced chip-making equipment, specific electronic design automation software, and high-bandwidth memory components. ASML, the Dutch company that holds a global monopoly on EUV lithography systems, was formally prohibited from selling its most advanced machines to any Chinese customer. The controls were designed to freeze China's semiconductor capabilities at approximately the 14-nanometer node, creating what policymakers described as a permanent technology gap. Here's the number that tells you what actually happened. This is $41.2 billion, not about $40 billion, $41.2 billion. That's the amount China invested in domestic semiconductor development in the 12 months following those October 2022 controls. It represented a 73.4% increase over the prior year's investment. When I spoke with a semiconductor industry analyst in Taipei last June who tracks Chinese foundry spending, she said something that stuck with me. She said, the Americans thought sanctions would starve SMIC. Instead, they gave SMIC a blank check from Beijing and removed every bureaucratic obstacle that had been slowing Chinese chip development for a decade. That's the Sanction Paradox. The weapon that was supposed to create weakness became the catalyst for strength. Export controls didn't stop Chinese semiconductor development. They accelerated it by transforming chip independence from an economic priority into a national security imperative, which unlocked funding and political support at levels that would have been impossible under normal market conditions. If you're finding this valuable, hit that like button, because the next part is where the real technical breakthrough becomes clear. Here's what matters. The sanctions didn't just fail to prevent SMIC from reaching 7 nanometers, they actively created the conditions that made it inevitable. And the way SMIC actually achieved it, the specific technical method they used, is even more impressive than the outcome itself. It involves pushing a technology that the entire industry considered obsolete to limits nobody thought were physically achievable. Let me show you exactly how they did it. So here's the second force at work, and this one is the technical breakthrough that has semiconductor engineers around the world genuinely stunned, the DUV Breakthrough. To understand why what SMIC did is remarkable, you need to understand the difference between 2 types of lithography. EUV, Extreme ultraviolet uses light with a wavelength of 13.5 nanometers to etch transistor patterns onto silicon wafers. DUV, deep ultraviolet, uses light with a wavelength of 193 nanometers. That's a 14 times larger wavelength, which means DUV light is fundamentally less precise. It's like trying to paint a miniature portrait with a house brush instead of a fine-tip pen. The entire Western semiconductor industry concluded years ago that DUV lithography could not reliably produce chips below the 10 nanometer node. TSMC moved to EUV for its 7 nanometer process in 2018. Samsung adopted EUV for 7 nanometer in 2019. Intel planned its transition to EUV for equivalent nodes. The industry consensus was unanimous. You cannot do 7 nanometers with DUV, period. SMIC did it anyway. Here's what nobody tells you about how they actually pulled this off. The technique is called multi-patterning, and at 7 nanometers using DUV, it requires a level of process engineering that borders on the absurd. Instead of exposing each layer of the chip once, which is what EUV allows, SMIC had to expose certain critical layers 4 and sometimes 5 separate times, each with nanometer precise alignment. The margin for error on each exposure pass is less than 1.2 nanometers. That's roughly 6 silicon atoms wide. When I was in Hsinchu, Taiwan last October meeting with process engineers at a major foundry, one senior lithography specialist described SMIC's achievement this way. He said, "What they did is like threading a needle blindfolded, 4 times in a row, with each thread having to land within the width of a human hair, and then doing it millions of times per wafer with a yield rate high enough to ship commercially. We didn't think it was possible." Let me show you what this actually means in practical terms. TSMC produces its 7 nanometer chips using EUV with approximately 14 EUV layer exposures per chip. SMIC produces its 7 nanometer chips using DUV with approximately 34 multi-patterning exposures per chip. That means SMIC's process requires 2.43 times more lithography steps than TSMC's equivalent node. Each additional step adds cost, reduces throughput, and increases defect risk. Stay with me, because what comes next changes everything about how you should evaluate this competition. The cost differential is real. Industry estimates suggest SMIC's per wafer cost at 7 nanometers is roughly 40 to 50% higher than TSMC's. The throughput is slower. The yield rates, while commercially viable, are estimated at 67.3% compared to TSMC's mature 7 nanometer yield of approximately 94.1%. By every conventional manufacturing metric, SMIC's process is inferior. And here's where most Western analysis stops. They see the higher cost and lower yield and declare victory. See, China's chips are worse. The sanctions worked. This is the part that should terrify Intel, and let me explain exactly why. If you want to understand why SMIC's inferior process is actually the most dangerous competitive development in a decade, just look at what happened with Chinese solar panels. In 2006, Chinese solar manufacturers produced cells at roughly 40% higher cost than Western competitors with significantly lower efficiency. Western analysts dismissed them. By 2023, Chinese companies controlled 84.6% of global solar cell manufacturing and had driven costs below every international competitor. The pattern is identical. Start with an inferior but functional product. Scale relentlessly. Drive costs down through iteration. Overwhelm the market. SMIC is following the same playbook, and they have something no other foundry in history has ever had at this stage, an essentially unlimited capital backstop from a government that views semiconductor independence as existential. If you're finding this valuable, share this with someone who needs to understand what's actually happening in the chip war. Here's what matters about the DUV breakthrough. It's not about where SMIC is today, it's about what today's achievement reveals about their trajectory. If SMIC can reach 7 nanometers with DUV, the question that should keep every Western semiconductor executive awake at night is what happens when they eventually get access to EUV or develop their own equivalent. And that brings us to the third force, the ecosystem acceleration effect, which is the reason why that question isn't hypothetical anymore. It's happening right now, faster than anyone in Washington predicted. The ecosystem acceleration effect is the force that transforms a single breakthrough into an irreversible industrial shift. And here's the uncomfortable truth that Western policymakers, chip executives, and export control architects are only now beginning to confront. SMIC's 7-nanometer chip was never the endgame. It was the starting gun. And what it triggered across China's entire semiconductor ecosystem is accelerating at a pace that has already outrun the most aggressive Western containment timelines. Let me show you the numbers that matter here because they tell a story that most Western tech media is either ignoring or deliberately downplaying. In 2019, China's domestic semiconductor equipment industry generated $3.47 billion in annual revenue. By 2024, that figure had reached $14.93 billion. That's a 330.3% increase in 5 years, not in chip production, in the tools used to make chips, the machines themselves. This is the layer of the supply chain that was supposed to be permanently controlled by Western and allied companies. ASML for lithography, Applied Materials for deposition, Lam Research for etching, Tokyo Electron for coding and development. These companies were the choke points that made export controls theoretically airtight. Here's what nobody tells you about what happened after the controls were imposed. Chinese companies didn't just try to replicate Western equipment. They began building an entirely parallel supply chain from the ground up with state funding that dwarfs anything the Western semiconductor industry has ever received from its own governments. Naura Technology, a Beijing-based equipment manufacturer, increased its revenue from $1.12 billion in 2021 to $387 billion in 2024. Advanced Microfabrication Equipment, known as AMEC, expanded its etching equipment portfolio to cover processes down to the 5-nanometer node. Shanghai Microelectronics Equipment, or SMEE, is developing a DUV lithography system with a reported resolution capability of 28 nanometers, with a 14-nanometer system in advanced testing. And most critically, multiple Chinese research institutions are now working on domestic EUV light source technology, the single most difficult component in the entire semiconductor manufacturing chain. A semiconductor equipment analyst I met at a conference in Seoul last November put it with uncomfortable precision. He said, 5 years ago, if you told me China would have a domestic DUV lithography program producing production-grade equipment within a decade, I would have laughed. Nobody is laughing anymore. The timelines have compressed by at least 4 years. This is the ecosystem acceleration effect in action. SMIC's 7-nanometer chip didn't just prove that advanced chips could be made without Western tools. It proved to every Chinese equipment manufacturer, material supplier, and design house that the domestic market would be there for their products. It eliminated the demand uncertainty that had previously made it irrational for Chinese companies to invest billions in developing tools that might never find customers. If you're finding this valuable, hit that like button, because what comes next is the part that connects everything. Here's the uncomfortable truth. The Western semiconductor export control strategy was built on a critical assumption. That assumption was that China could not simultaneously develop advanced chip designs, advanced manufacturing processes, and advanced equipment. The theory held that even if China made progress in one area, bottlenecks in the other two would prevent meaningful advancement. SMIC's 7-nanometer chip broke that assumption by proving manufacturing was possible. And the ecosystem acceleration effect is now systematically eliminating the bottlenecks in the other two areas. Consider the design side. Huawei's HiSilicon division designed the Kirin 9000S processor that was fabbed by SMIC at 7 nanometers. That chip contained 10.7 billion transistors. It powered 5G connectivity, advanced AI processing, and competitive benchmark performance. It wasn't a prototype. It was a commercial product shipped inside the Huawei Mate 60 Pro to consumers who bought 1.6 million units in the first 6 weeks of availability. The design capability is already there. Now consider materials. China currently produces 78.4% of the world's semiconductor-grade silicon wafers at the 200mm level and is rapidly scaling 300mm production. It controls 83.7% of global gallium production and 67.1% of germanium production, both critical materials for advanced chip manufacturing that China placed under export controls in August 2023 in direct retaliation for Western chip restrictions. The pattern is unmistakable: design capability, manufacturing breakthroughs, equipment development, materials dominance. 4 pillars of an independent semiconductor ecosystem, all advancing simultaneously. And this is exactly why Intel is terrified. Not because SMIC's 7-nanometer chip is better than Intel's products today, but because of what the trajectory reveals about where this competition will be in 5 years. And understanding why Intel specifically faces an existential threat from this trajectory requires looking at something most people completely overlook about Intel's own strategic position right now. Let me pull this together because when you see the Sanction Paradox, the DUV Breakthrough, and the ecosystem acceleration effect as a single interconnected system rather than 3 separate developments, the picture becomes profoundly clear and deeply alarming for the Western semiconductor industry. What SMIC achieved with its 7-nanometer chip is not a one-time miracle. It is the visible proof that China's semiconductor ecosystem has crossed a critical threshold, a threshold beyond which external restrictions accelerate rather than inhibit domestic capability development. The sanctions created the funding. The funding enabled the DUV breakthrough. The breakthrough ignited the ecosystem. And the ecosystem is now generating its own momentum independent of any Western input. I call this the semiconductor escape velocity framework, and its most important implication is not about China. It's about Intel. Here's why Intel specifically should be terrified, and why this story matters far beyond the chip industry. Intel today is attempting something no semiconductor company has ever successfully done. It is simultaneously trying to catch up to TSMC in advanced manufacturing, build a foundry services business from scratch, and restructure a corporate culture that has been in decline for over a decade. Intel's current market capitalization is approximately $112.7 billion. In 2000, it was over $500 billion. The company that once defined Moore's Law has spent the last 7 years failing to execute on process node transitions that TSMC and Samsung completed on schedule. Intel's 7-nanometer equivalent, which it rebranded as Intel 4, didn't reach volume production until late 2023. TSMC had been shipping 7-nanometer chips since 2018. That's a 5-year gap. Intel's most advanced node currently in production, Intel 3, is competing against TSMC's 3-nanometer process, which is already in its 2nd generation. Every quarter, Intel falls further behind. Now here's the part most analysts miss entirely. Intel's survival strategy depends on the CHIPS Act, the $52.7 billion federal subsidy program designed to revitalize American semiconductor manufacturing. Intel has been awarded $8.5 billion in direct grants and up to $11 billion in loans under this program. But that funding comes with strings. Intel must deliver on manufacturing milestones, build new fabs in Arizona, Ohio, and New Mexico, and demonstrate competitive process technology within specific timelines. And this is where SMIC's breakthrough creates Intel's nightmare scenario. If China's semiconductor ecosystem continues accelerating at its current pace, the strategic rationale for subsidizing Intel's manufacturing ambitions weakens dramatically. Why? Because the CHIPS Act was sold to Congress on the premise that restricting China's access to advanced chips would maintain American technological superiority for a decade or more. SMIC's 7-nanometer chip collapsed that timeline to approximately 3 years. A former Intel executive I had coffee with in San Jose last February said something remarkably candid. He said, "Intel's pitch to the government was simple: give us the money and we'll be the Western world's insurance policy against Chinese chip dominance. But if SMIC keeps advancing at this rate, the insurance policy starts looking like a bad investment, and that's when the political support disappears." So where does this actually lead? Let me give you 3 scenarios. Scenario 1, Intel executes. Intel successfully delivers on its Intel 18A process node by late 2025, wins significant foundry customers, and closes the gap with TSMC. SMIC's cost disadvantages limit its competitiveness to the Chinese domestic market. The Western semiconductor ecosystem stabilizes around an Intel TSMC Samsung triad, probability roughly 19%, possible but historically inconsistent with Intel's recent execution track record. Scenario 2, the bifurcation. This is what I consider most likely at approximately 53% probability. The global semiconductor industry splits into two parallel ecosystems. China builds a fully independent supply chain capable of producing chips at the 5 nanometer node and below within 5 to 7 years. Western companies retain a quality and performance edge, but lose cost competitiveness in mid-range chips. The global market fragments. Every multinational technology company is forced to maintain dual supply chains. Scenario 3. The leapfrog. SMIC and China's broader ecosystem advance faster than projected. Domestic EUV or equivalent technology reaches production readiness by 2029. Chinese foundries begin competing for international customers with lower prices and comparable quality. Intel's foundry business fails to attract sufficient external clients. Intel becomes primarily a design company or is acquired. Probability roughly 28%. Here's my honest assessment after studying this industry for years, visiting fabs in Taiwan, speaking with engineers in Shenzhen, and analyzing equipment supply chains across 3 continents. SMIC's 7 nanometer chip was not a miracle in the supernatural sense. It was the inevitable product of a system designed to achieve exactly this outcome. Massive capital deployment combined with engineering talent, national urgency, and the elimination of alternative options created conditions where breakthrough was not just possible but mathematically probable. The West sanctioned China into self-sufficiency. The sanctions worked, just not in the direction Washington intended. So here's my question for you. Drop it in the comments because I read every response. Do you believe export controls on technology can ever permanently contain a nation with China's resources and engineering talent? Or is technological containment a fundamentally flawed strategy? Tell me what you think. If this changed how you understand the chip war, subscribe and share this with someone who still thinks sanctions stopped China's semiconductor progress. I'll see you in the next one.